અત્યારે જેનિયા પછી ફોન મૂક્યો તને ફોન કર્યો તો તને 21 મિનિટ મારો અલગ અલગ ફોન કરવાનો
Alrighty, it is 10:05, and I think everyone who is intending on joining us is probably here by now. So I think I'll get started. But before I get started, I want to make sure that everyone can hear me. So I'm going to go to the participants menu. And could I get some kind of confirmation in the chat that, let's see, I'll turn my video on so you guys can see the person behind the screen. If you guys can hear me, could someone indicate that in the chat for me? Looks like I'm getting some 4 thumbs up. I think that's a good sign. Let's see. I'm a stranger to Zoom. I'll go to the chat. All right, I'm getting thumbs up in the chat too. Thank you, guys. So, yeah, for the intro, I'll turn my video on and I'll turn it off later so I don't distract myself. But let's see, I'll go to the next slide. I can. There we go. So this is the August vapor tutorial, and basically, we're just going to run through Vapor, and I'll start by kind of describing what Vapor is. You guys, if you're here, you probably already know that Vapor is a desktop application for 3D visualization. It's an open source application, and it's mostly geared towards the geophysical science domains, but we do have some users in astrophysics, some in chemistry, But really, we are dedicated to serving the atmospheric and geophysical science community. You may or may not know there are a lot of options when it comes to 3D visualization. And so a good question would be, what room is there in the world for yet another software package for doing kind of the same thing that other software packages do? And the reason that there is room for Vapor is because of our dedication to the geophysical science community. All of 3D visualization is difficult. It's very hard compared to 2D visualization, specifically because the amount of data that you're working with is about an order of magnitude higher. And filtering out that data to show the artifacts and observables is the trick. And so we're going to be going through that today with Vapor. Vapor is also cross-platform. We have installers for OS X, Windows, Ubuntu, and CentOS. And our website is www.vapor.ucar.edu. And I want to take a quick detour and show you guys the website real quick, because this will be your reference point for basically your education outside of this tutorial if you have questions and that kind of thing. So www.vapor.ucar.edu. And here are the links to our downloads. If you click on that, you can see our current release 3.6.0 and click on the download here link. We'll have a quick survey that you guys can fill out if you want, or you can just skip it if you like, but the information is good. So please fill it out if you have the time. And then it'll just redirect you to our GitHub page where our repositories and releases are. At our GitHub page, you can go to the Issues tab and file new enhancement requests or bug reports. And so this is kind of the way that we operate for developing Vapor. We look at the issues, we prioritize them, and then we submit pull requests depending on how they were prioritized for the next release. Our next release, by the way, is 3.7, and we're hoping to get that out in a couple of weeks. And so I'll be demonstrating Vapor 3.7 today with a pre-release installer. But if I go back to our website, kind of the information, the core of the information is our read the docs page. So if I go to our documentation link, here you can find download links to our current release, sample data. So if you want to, well, it's probably too late to download this data right now, install Vapor and follow along, but this will be recorded. So if you want to follow along with this data set that we'll be working with today, you should be able to find it in this sample data table right here. You can also find installation instructions for each platform, a quick start guide. You won't need the quick start guide because this tutorial will serve as that. Getting data into Vapor, this is probably the hardest part of using any 3D visualization application. Massaging your data so that the application can actually read it. So in this section, we cover all that information. And then there's our usage guide. Up at the top, I'll click on the renderers. And basically, Vapor consists of roughly 10 or 11 algorithms that we call renderers. And each renderer will color your data and apply opacity to it in different ways. And so I'm going to be demonstrating not all the renderers, most of them today. But if you have a question or I go too fast, you can go to the renderers section and then, for example, click on the volume renderer. And you can see a YouTube video where we step through all the parameters in the volume renderer, and we have a little bit of a text. But I don't know, I usually find the YouTube videos to be the most information-rich way to learn Vapor, just because you can see somebody actually working with it and where the buttons are. It's kind of hard to describe where the different parameters are with text versus a video where you can actually see it being done. And yeah, I think that's all I'll really cover. Finally, there's like get help on our forum, vapor.discourse.group. If you guys have any questions, this is where to go. I might post, I'm going to be covering a new Python API today that allows you to use Vapor through a Python script. And if you guys want to get an early release on that, I might post a link on our forum. So I guess keep your eyes peeled for that if you're interested. So yeah, this is the information hub where you're going to go for any help or questions you might have after the tutorial. So with that being covered, let's see if I can go back to my presentation. There we go. All right, so that's kind of the intro. I do want to talk about what we're looking at over here on the right, and I think I'm going to stop my camera because I think I'm sharing this window that's obscuring the simulation that we're seeing over here on the right. So this is an idealized simulation of the Drake Passage in between Antarctica and South America. And what we're seeing here is a volume rendering of kinetic energy going through the Drake Passage underneath a two-dimensional rendering of the bathymetry of the data. And this is being done in CGD right now, and why it's important is because the Drake Passage is has the most turbulent waters in the entire world between the Pacific and Atlantic Oceans. And it generates these vortices that you guys can kind of see in yellow. And these vortices can travel across the entire planet, and they're biologically important because they are responsible for transporting coral larvae. So coral reefs transport their offspring through these vortices. And these vortices can last for years at a time, traveling throughout the entire planet. And some scientists have found that there's complete evolutionary cycles, like new species can be evolved during the transport of these packages that float around the entire sea. And so again, that's a volume rendering of kinetic energy, basically how fast the water is moving. And let's see, go to the next slide. And here's another project we're working on with, well, the Vapor team is working on. This is a simulation of the East Troublesome Fire that happened in 2020, I believe. And it was one of the largest wildfires in Colorado history. It lasted for over 2 months, and there was a 3-day period where it quadrupled in size. And you can kind of see the perimeter of the fire approaching the town of Granby, which is to the south by that lake, and then Grand Lake is right in the middle of the scene. And one of the problems that they were finding is that people were not evacuating or following evacuation orders quickly enough. And so NCAR is conducting a case study right now, trying to better gauge how to get people to follow these evacuation orders. One of the things that we're going to try to do is use Vapor's Python API to run visualizations of real-time simulations of these wildfires, and then show those visualizations to people to see if they actually follow the evacuation orders. And so that's one view. Here's a view from Granby looking to the north. Again, what we're seeing here on the very bottom is a base map. We call it the image renderer. And so I'll show you guys how to acquire a base map for your study area and then apply a height variable to it. On top of that map, we have a Barb renderer, just simple wind barbs or arrows showing the wind directions, colored by wind speed. The wind speed is a derived variable, so it was not in the original data set. So we have a Python calculation engine that allows you to create new variables based on the ones that are currently inside your data set. On top of the image, we see the fire perimeter, and that's a two-dimensional variable superimposed on top of the image. And the smoke is a volume rendering. A volume rendering is basically just applying color and opacity to the entirety of your data domain. And I think those are the renderers that we're seeing at play there. This is a perspective from Grand Lake, and this is where they were having trouble getting people to evacuate. I think roughly 400 structures were burned down during this fire. And then finally, I think we have one more perspective from way up high in the sky from Estes Park. And yeah, a little bit farther away. Didn't affect Estes Park as much as other locations, but that's the East Troublesome Fire. So the data set we will be working with today isn't East Troublesome. We will be working with a new data set of the Marshall Fire that happened last December that took out significant portions of the towns of Louisville and Superior, Colorado. Here's an image of the Marshall Fire looking to the north, I believe. And there are many reports of what is known as an atmospheric rotor, which is believed to drive this wildfire in the way that it did. And an atmospheric rotor is a phenomenon that is known as a hydraulic jump. And so if you're familiar with a weir is a structure that's used to control the flow of water or the water height. And what can happen with a weir is the water will flow over the top of the weir, jump down, and then create this vortex that is extremely dangerous. A lot of people drown in these things every year because once you're stuck in this vortex, your buoyancy is pretty much negative at that point, and you get stuck in this vortex. It's hard to get out of. And so an atmospheric rotor is the same kind of thing. You have the winds coming up over a mountain range, and you get a hydraulic jump that creates a rotor or a vortex along the mountain range. And then sometimes you get what's called a rotor cloud. And this is a picture of a rotor cloud. You can kind of see the helicity of the cloud as the rotor is spinning underneath it. And so the scientists I've spoke to that developed this data set are claiming, yes, there is a rotor in this simulation. And so I've been trying to find it for about a day and I haven't had luck. So I'm going to give it a crack today. Whether or not we find it isn't so much as important as just demonstrating the abilities of vapor. So that's the end of the intro. With that being said, the first thing to do is to load Vapor. So I've already installed Vapor, but if I go back to the website again, github.com/in_vapor, if I go to my releases here, there's a link to a weekly installer. So if you want an up-to-date installer, it's under weekly. You can see all the assets we currently have. I think the Windows build is broken, but CentOS, OS X, aka Darwin, and Ubuntu are available in weekly releases. And so basically just click on one of these links on our GitHub page, or if you want an official release 3.6.0, you can scroll down and just download one of these assets. And then once you install Vapor, at least on OS X, you'll be able to drag Vapor. I think by default, it just goes into your applications menu. Mine's at the top. I always have a shortcut at the bottom. And so I'm just going to click on that. And here we have an open session in Vapor, but you can see that it's all grayed out. There's nothing to do, and the reason for that is because we haven't loaded any data. There's really nothing you can do without having data. So the first thing we have to do is go to the File menu. And there are, well, if you go down to this Import section, this will list off the data formats that we natively support. WRF-ARW, NetCDF, that is CF compliant, and I'm going to speak to that after going through Vapor, because basically what this means is that there are coordinate variables that have certain attributes that Vapor can read in order to know what axis your coordinate variables pertain to, their units, and that sort of thing. We also support impasse data, brick of values, BOV, this is raw binary data. So if you have just a file of pure floating point values, you can load those as a BOV file as long as you generate a header that describes the structure of your raw data. We need to know things like the dimensionality on the X, Y, and Z axis, and that sort of thing. We have a particle renderer. I'm not going to cover that too much today. But if you have NetCDF files that describe particle data, you can massage them into this DCP format and render them that way. And then finally, there is the unstructured grid, aka UGrid data format. Another data format we support that is kind of unique to Vapor is the VDC. And the VDC is useful when your data is so large that Vapor becomes non-interactive. It can, if your data is huge, if your grid is massive, the response times that you're going to have with Vapor are going to be very slow. And so what VDC allows you to do is it applies a wavelet transform on your data that effectively, it doubles the data's footprint. So if your file is 1 gigabyte, a VDC will be 2 gigabytes, but the trade-off is that the VDC allows you to look at progressive levels of refinement of your data. So you can look at your data at a highly compressed ratio, or you can look at it at full fidelity. And so what you're probably typically going to do if Vapor becomes non-interactive is you can explore your data interactively at a high level of compression. And then once you think you have everything right, all your colors are okay, all of your opacity looks pretty good, then you can crank your data back up to perfect reconstruction, zero compression, press play and capture your images non-interactively and basically step away from your computer. Don't touch it until the animation sequence is complete. So those are the data formats, but we're dealing with WRF-ARW today, WRF-Fire to be exact. And so I'm going to, I clicked on WRF-ARW and I'm going to navigate to my downloads directory. Okay, here's my Marshall data set. This data set has two different components. I'm going to start with the Fire component. And I'm just going to simply select all my WRF files and click open. So here's basically the initial screen, still kind of a blank slate. We have our domain over here on the right in this black box we call the visualizer. I can right click my mouse to zoom out. I can left click to rotate the scene. And then the middle mouse button will traverse like such. By the way, if you're using Vapor, I highly recommend using a mouse. It's extremely difficult to use a trackpad, so a mouse is kind of imperative in my opinion. So like I mentioned earlier, Vapor is comprised of a series of algorithms called renderers, and we have to instantiate new renderers in order to draw things within our box. So I'll zoom in a little bit and click on this new button up here in the top left. And this will present us with a menu that lists off all the different renderers available in Vapor. And I'll just run through these real quick. Barb Renderers, we saw those in the East Troublesome Fire, just arrows demonstrating the wind vectors. Contours can be done on 2-dimensional and 3-dimensional fields. If you're doing contours in a 3D field, you can arbitrarily orient a plane that the contours will be drawn upon. The flow renderer supports two types of flow: pathlines and streamlines, and I'll be covering streamlines later. The difference between a pathline and a streamline is that a streamline is time invariant. So if you were to just draw a line through space that tracked the wind vectors, that would be a streamline. It's completely time independent. Whereas a pathline is time dependent. If you took a handful of feathers and threw them into a tornado, the path that those feathers would take would be analogous to a path line. And so I don't know if there's some time at the end, I can show basically what I just said, path lines advecting into a tornado if there's time at the end. Image is basically a base map. We'll be doing that today. Isosurfaces are analogous to contours, but they're within an entire 3D space. So it's just a surface that follows a single value of a variable through 3D space. So every point along this, this surface here is one value of a variable, and likewise for that surface and that surface. The model renderer allows you to bring in 3-dimensional models into your scene. So we have an STL file in this example of a windmill and then a volume rendering of turbulence behind it. And so there's some good resources online for free models, like for things like wind turbines and that sort of thing. I think SketchUp may have a model of the NCAR Mesa laboratory and all sorts of, there's a lot of resources out there, but I'm not going to go into the model renderer today. The next one down is the particle renderer, and I touched on this earlier. The particle renderer requires a certain data format, and there are no particles in this data set, so it's disabled. We can't use that one today. The slice renderer is kind of similar to the contour renderer in that you can just describe an arbitrarily oriented plane, and then we will render a variable along that plane. 2D data is basically a 2-dimensional variable, typically at the base of your map. Fire area is the variable that I'll be using the 2D data renderer with today. And that's going to be the first one I start off with, but just really quick, mention the volume renderer. The volume renderer applies opacity and color throughout the entire volume of your data. And we'll be using that for smoke. It's usually good for things like smoke, vorticity, and we'll be using it today for smoke. So the renderer I'm going to start off with is the 2D data renderer. And I'm going to, actually, before I do the 2D data renderer, I want to get a base map first. So I'm going to click on New again and click on my image renderer. And you can see here I've instantiated two different renderers in Vapor. In order to control them, we have this table that lists them. In order to control them, all you have to do is click on the renderer that you're trying to edit, and then all the parameters that apply to that renderer will show up in this section on the bottom left. So if I go to my image renderer, I'm now controlling the image renderer. And if I go to 2D data renderer, there are the parameters for that. So we go back to my image renderer. I'm just going to go ahead and start off by turning it on. So there's this enabled checkbox, and there's my initial image rendering. The image renderer in Vapor is kind of different than others because it uses a geotiff and just paints it on the bottom of the scene. And so by default, if I go over here to the Appearance tab, you can select your geotiff file. And Vapor comes bundled with a couple of images that are pretty coarse in resolution, especially for a simulation like this. This is a pretty high-res simulation. And so what we're going to want to do is get a new geotiff. If we bundled higher resolution images in Vapor, Vapor would just be too big to distribute. And so this calls for a custom image. So what I like to do, my favorite resource for geotiffs to use in Vapor is, let's see, I can find my bookmark menu. NASA's Worldview, EOS-DIS Worldview. This is basically a web map service that contains tons and tons of satellite data. And I believe the Landsat, Landsat 8 and 9 is what we're looking at here. And this is, I don't know, typically what I use. It's nice because you have a scroll bar down here that allows you to select the time of the satellite imagery. And so the Marshall Wildfire was on the 31st. But if I go over to the 31st, the problem with satellite data is that the satellite coverage doesn't always overlap with the date that you're interested in. So on the 31st, the satellite wasn't looking at Boulder County, but I think if I go back to the 28th, this is approximately what I want. So here we have Stanley Lake down here. You can kind of see US 36. Here is Boulder. And if I zoom in more, this is the Marshall Mesa Marshall Reservoir, and here's where the burn scar came through. So to acquire my geotiff, there's this camera button up here. I will take a snapshot, expand it, and I will go for the highest resolution per pixel image. That is a 30-meter snapshot. The format needs to be geotiff. And then I'll just make it a little bit bigger like that, and I'll download it. And while that's going, I actually have a previously downloaded image that I'm going to use, but that was just demonstrating how to go about acquiring geotiffs from the EOS-DIS Worldview server. So back to my image renderer, I'm going to select the geotiff that I downloaded earlier, go to my downloads directory, and it looks like I'm going to go with the old one because I'm certain it works. Oh. That shouldn't happen. So interesting. What I'm going to do now, I believe my source build, I've seen that happen before, but my source build does not exhibit that behavior. So I'm going to do bin vapor.app. Yeah, I thought I fixed that this morning, so that's a little surprising, but let's see. Restart Vapor from my source build, file, import once again, WRF ARW. Downloads, actually it should be here. Try that again, image renderer. I think OS X might be scrutinizing Vapor right now. There we go. Appearance, select my snapshot. There it is. Okay, so I will get to that bug later today. But there's the image that I downloaded from the Worldview server. The problem right now, though, is that it's kind of flat, and we all know that there is mountainous terrain over here on the left. And so what I'm going to go do now is go to the Variables tab, and I'll explain what these tabs, how they conceptually work with an actual renderer. The image renderer is a little bit different. So basically, I just want to apply a height variable, and I can do that in the Variables tab. I'll just speak to it real quickly. There's going to be at least 3 tabs for every renderer that pertain to what we are rendering. That's the variables tab. The appearance tab tells us, or tells Vapor how to render your renderer. That's the color and opacity parameters, or the image file in the case of the image renderer. And then the geometry tab is where you're rendering to. So if you want to render to a specific region, you can edit your region like so. So I just increased the maximum extent on the x-axis with this slider, and you can reduce or increase the area you're rendering to through the region tab. And why that's useful is because you may not be interested in the data in certain regions of your data set, and you can reduce the amount of data that is sampled by reducing your region, which will make your renderers go faster. And I'll be showing that a little bit more in a bit. But what we're looking for is a height offset. And so that would be done in the variables tab. Again, variables is what, appearance is how, and geometry is where. So variables, I will select HGT. And this is quite a large data set. You can see under this data fidelity section, if you're using the VDC, and we're not, we're reading raw WRF data. So this is pretty much, these are all no ops. But if we were looking at VDC, here's where we would control the fidelity or the compression of the data that we were looking at. So our height variable has been registered, but typically with 3D visualization and with atmospheric simulations, atmospheric simulations, the X and the Y axes tend to be much, much larger than the Z axis. And so what typically ends up happening when performing a visualization is a stretching of the Z-axis to give more emphasis on the 3-dimensionality of your rendering. So to do that, I'm going to go to the Scene tab, which kind of contains universal parameters that don't apply to any specific renderer, but they do apply to the entirety of your current session in Vapor. You can turn on annotations, annotate them with latitude and longitude as opposed to meters on the ground. Let's see, we can bump that up a little bigger, add significant digits, and that kind of thing. But what I'm really looking for is not annotations on my axes. I'm looking to stretch my Z-axis, which is done through the Viewpoint tab. And up at the very top, we have a transform table that pertains to a certain data set. Right now, we've only loaded one data set. We'll load another one in a minute. But for now, I'm going to scale my Z-axis. Let's see, is 2 sufficient or 3? Let's call it 3. All right, that looks pretty mountainous and good enough for me. So back to my renderers tab. One thing that is bothering me right now is how the image is being kind of dragged down to the base of the domain. So what I'm going to do now is go to my geometry tab, and I'm just going to nudge my y-axis up a bit. Whoops, there, it's processing there. And so now we're clipping that edge and giving it a little bit of a nicer effect, in my opinion. And I'll do the same thing for X as well. Okay, so that's the basics of the image renderer. We now have a context for where we are in space. The next renderer I'm going to do is a 2D renderer because I want to get the fire area superimposed on top of my image. So I'm going to click on the new button. I have my list of renderers, click on 2D data, click OK. Let's see, re-maximize. And then I will go to my variables tab to determine what we are rendering. And so here are the list of 2-dimensional variables in my data set. I'll click on fire area. And let's see, should I turn it on? I fear it's going to take a while to render, but I'm just going to turn it on. Let's see. And then once this activates, we will have default settings. Well, right, there is no height variable being applied, so I have to do that as well. So like the image renderer, I can apply a height variable to the 2D renderer in the same way. Yeah, this would have been a good opportunity to demonstrate the VDC. I could do this at a lower fidelity and it wouldn't be taking quite so long. But what I will do next is probably reduce the region of the 2D renderer. Yep. So see, this is a phenomenon called Z fighting. The image renderer and the 2D renderer are being drawn at precisely the same location. And so I have to offset the 2D renderer by bringing it just a notch up above the image renderer. So again, I'm going to go to the geometry tab, which tells me where I'm rendering to. I'm going to translate it on the Z-axis by 50 meters. So I'm going to shift this thing 50 meters up, and now it's completely covering up the image. What we are going to want to do is go to the Appearance tab. And yeah, this data set is interesting. So yeah, let's talk about the Appearance tab, because this is kind of the real heart of Vapor, you know, how your renderer is being depicted or painted onto the screen. Most, if not all renderers, well, except for the image renderer, have this thing that's called the transfer function. The transfer function basically is what is applying color and opacity to whatever renderer you're currently operating on. At the left, at this left line edit over here, you can see the minimum value of our current variable. Right now we're looking at fire area. And over here on the right is the maximum value, this wild number right here. I don't know where that came from. I'm wondering if that's a missing value or something else, but it's completely nonsensical. So I'm just going to call that 1. And then, okay, so that's more reasonable. We can now see the burn area of the Marshall Fire at this current time step we're on, the initial one. And we can actually start working with the color and opacity controllers. The first thing I'm going to do is, well, I have to explain what the transfer function is. What are we looking at? This is a distribution function, basically, of the current variable. It's basically a histogram showing the values of the variable and how they are populated between the range we have set, which is between 0 and 1. And right here, you can see we have this impulse. We have a ton of values over here at blue. All those values we can see over here in the visualizer painted as blue according to this color control point. Looks like we have like 1 pixel in red over here at the right, which is our burn area. And so this data distribution is pretty much like a 1 or a 0, kind of binary. We have an impulse on the left, a pixel on the right. And so what I'm going to do is right-click on the histogram. And instead of scaling it in a linear fashion, I'm going to do it in a logarithmic fashion. Maybe this, okay, so once I scale it logarithmically, we can see there are data values in between this far red value of 1 and this dark blue color over here on the left. And basically all of these variable values are being colored according to the color bar value beneath them. If I zoom way in on the burn area, you can see there are these white values that are being applied colors like right around this area. What I can do is I can take these color control points and drag them, and you can see how I'm really squeezing that white area in like so. And you can do the same thing for the red. And this isn't the most interesting example, but it does demonstrate the point. So one thing that I'll do is I will also double click on the color bar, and then you can create new control points by double clicking on this color bar and delete them by double clicking as well. Since I don't care so much about this blue area, I do care about the burn area. What I'm going to do is apply opacity to the blue section. And to do that, there is a series of color control points that overlay on top of our distribution histogram. I can grab those control points and drag them down. And the further I drag them down on the y-axis, the more transparent they become. So high on the y-axis is opaque, low on the y-axis is transparent. For the burn area, I don't think this is the greatest color palette though. I mean, it's just saturated red. And so what I'm gonna do is click on this gear icon and load a new color map. And so we can, well, just to cover this in its entirety, you can change your interpolation methodology for the color bar, which is probably an advanced feature and most people don't care about. You can reverse it. So if I do that, instead of seeing red burn area, now we have blue. You can save color maps that you've custom created. And just emphasis, you can save and load color maps, and you can save and load transfer functions. The transfer functions will also take into account the opacity values you've set. Color maps are just purely color bars. I can load a built-in color map. And so we have three sets of color maps: diverging, which are good for modal distributions. So if you have like a witch hat curve, it's good to highlight the tails of that distribution and then have them converge in the middle with white. But you can tell my current histogram is not a modal distribution. It's more of a sequential distribution. There's highlighting distributions, but this is really sequential. And so I will pick this color bar at the top called black body. And I think what I want to do is right click on the color bar, reverse it. And then I want to mute the black like so. And whoops, whoa. There we go. And then probably, I'm going to add, I'm just going to drag this color control point. Whoops, not too far over, but just enough like so. So we can kind of get an idea of what the fire burn area, where the burn area has been and where it is propagating to. Maybe turn that black a little darker. So that is the 2D renderer. We now have an image renderer determining where we are in space, the 2D renderer showing a simple 2D variable. The next renderer to show will be the volume renderer. So we need to get some smoke on top of this. So what I'll do is I'll click on new. I will double click on, or just click, I can double click on volume, or I can click volume and click OK. And the volume renderer pretty much behaves in the same way that the 2D renderer does in terms of its controls. The algorithm that it follows is called ray tracing. And basically what a ray tracer does is it casts imagine if you were to cast a laser through every single pixel on this screen. And along that laser, you would be sampling data values up until you get a point where you've reached a completely a point of maximum opacity. At that point, you stop sampling and you have your pixel value. So basically, if you have a 4K monitor, you would be casting 4,000 lasers through the data domain and sampling along those lasers for each pixel. Is kind of how ray tracing works in a nutshell. So I'm going to zoom out a little bit. And ray tracing is a more expensive operation than just drawing a texture like we do with the 2D renderer. So with the volume, I'm going to start, before I even turn it on, I'm going to go to the geometry tab where I see my red bounding box. I'm going to reduce the region that I'm rendering to, so I'm not sampling so much data and I get a little bit more interactivity. Yeah, and you can tell it's still kind of slow with a data set of this size. I think, yeah, it's about 2,000 on X and Y, and then on Z, I don't even remember. But again, it would have been nice to convert this to VDC. But that's all right. We'll just reduce the region and hopefully, let's see, I don't think I need to be so high on the Z axis, so I'll bring it down on the Z. Okay, so now we will be volume rendering from within this box. And I can also control the region kind of visually by right-clicking on these square boxes. So there's two ways to do it. You can click on the square boxes or through these sliders in the control panel over here. All right, I'm going to call that good. So that's the region I will be volume rendering to. And let's just turn it on and see what we got. A big opaque box. And that's because if I go to my appearance tab, is this right? It looks like it's going through the ground. Yeah, there is an issue here. So, yeah, we do have a ticket filed on this. This should be matching the surface. So what I have to do is go back to my geometry tab, and I think I'm going to have to translate the volume by 1,400 meters, bump it up. Is it still going through the bottom? Let's call it 1,450 to translate it and just bump it right at the surface. So our volume rendering is completely opaque. because we haven't applied any opacity. We can't see through anything because all the data values along this wall are occluding all the data values within this brick. So I'm not sure what variable we're looking at too. pH, that's not an interesting one. Fire smoke is the smoke variable, so I'll pick that. And what we're going to see as we apply opacity is that the rendering time is going to take even longer because these lasers that we're shooting through our pixels are going to be sampling more data. Right now, each laser immediately stops at this wall. We're not sampling any data through the volume because we hit maximum opacity immediately. So if I go to my appearance tab and apply opacity to these most populated values, our rendering is going to take a little longer. Maybe, I don't know, maybe we cached the data. It doesn't seem like it's taking as long as I thought it would. But there's a basic volume rendering of our smoke field. Are we getting some depth issues? Yeah, so sometimes the ordering, well, that looks actually right to me. Sometimes the ordering of the renderers gets backwards, and so sometimes you have to turn them off and turn them on in order to get the correct coloring. But I see the smoke on top of the 2D renderer. It looked like the 2D renderer was being painted on top of the volume, but I just think that's just the way the data is. Unless, is this? Yeah, I think the smoke is just at the periphery of the fire area, which makes sense. That's where the smoke would be emanating from. I'm going to go ahead now and load a better color map because blue smoke doesn't really make sense. So click on this gear icon, load transfer function, and let's see, downloads, actually go to this directory, fire.tf3, which I think is a variation on the black body color map that we used for the 2D renderer. And there it is. This is the color map that I think I used for the East Troublesome Fire. Looks like smoke or close enough to it. And that's the basics of that. So we've done 3 renderers with this data set. This is the fire component of the WRF-Fire simulation. There's also a meteorological component that contains the wind fields. And so with Vapor, you can load multiple data sets simultaneously. Like for example, if you had a ocean simulation, you could render a atmospheric simulation on top of it and look at the interface between the two and visualize multiple data sets that way. So what I'm going to do now is I think I'll demonstrate the whole VDC thing. So if I open up my terminal, and let's see, if I go make this bigger so everyone can hopefully see it. I'm going to navigate to my data directory. So cd into downloads, I'll go. And then the Marshall Fire is the one we want. Okay. So we loaded data a minute ago from the fire directory. I'm going to go into the MET directory, and this contains our meteorological files. When you install Vapor, Vapor is going to come with some command line utilities that'll help you convert your data into VDC. And so what we're going to use for the WRF data is called 2 tools, WRF VDC create, and then WRF 2 VDC. So if I go to, or if I ls my applications, Vapor, contents, Mac OS, and OS X, when you install an application, gives you this very long installation path. But if I do an ls on this installation path where Vapor got installed, we can see my WRF VDC create tool and WRF 2 VDC. And basically what these tools are doing is WRF VDC creates a metadata file that Vapor uses to understand the structure of the wavelet compressed variable values in your data set. So this is a header file with metadata, and then WRF 2 VDC actually performs the wavelet transform and creates the data set that is twice the size on disk as your original set. So the first step is to do WRF VDC create. So Vapor can generate this metadata file to understand the structure of your data. And then all I have to do, I believe, is pass in my data files. So that's WRF out with an asterisk to encapsulate all of them. And then the output file name, I'll call this met.vdc. And then I have to, it's not my system path, so I will just copy the full path. And then here's our met.vdc file. Step number 2 is basically the same thing, except instead of WRF-VDC create, I'll be doing WRF2VDC. And there we go. Vapor's now doing its wavelet transform on all the values. And I think this is going to take a while. So I cheated. I have in the VDC directory, I've already done the wavelet transform on these. And so what I'm going to do now is go back to Vapor and get those data files loaded by going to File, Open VDC, again, not importing, but we're doing Open VDC. And then navigate to my Met directory. And then I put my VDC files here. And here's the basically the output of what we just created with WRF-VDC create that created this VDC file. And then the wavelet compression is stored within this directory that has all of our variables with the wavelet compression algorithm applied to them. So I will click on Marshall met.vdc, my header file. I will load it as a new data set. And now that I've done that, I'm going to have to stretch it on Z like we did for the fire portion. And so if I go to my scene tab, you can see in our data set selector, we now have Marshall met.vdc alongside WRF-out, the WRF-Fire files. And so on that, I believe, did we do 3? I think we did 3. But if there's a misalignment, we can come back and fix it. And we're not going to see anything right now because we haven't instantiated any renderers with the VDC data set yet. So in order to do that, I'll click on New once again. And our data source, we get to pick up here. I'll click Marshall met.vdc and I'll do wind barbs. Okay, so now I'll start off in my variables tab just to go show you guys what's there. The Barb Renderer is a renderer that can operate on 2-dimensional and 3-dimensional variables. And to do that, we have this combo box right here. I'm going to do 2D variables because I want to show surface winds along the image. And so by default, Vapor is going to pick the first variable that starts with a U for your X field of your wind variables, and the first variable that starts with a V for your Y wind fields. You can color map barbs by different variables. I think by default, we look for temperature. But I'm just going to go ahead and actually, I need to apply a height variable. Let's see. So do that as well. Okay, and when I turn it on, cross my fingers, I should see wind barbs superimposed on top of my image. And wow, they are not. That's that height bug, I think, biting us again. So once again, I will go to my geometry tab and this is interesting. Is this really 2D? Yep. Okay, let's just, we'll have to cheat and knock this down by 1400. I'm guessing that might do it. Not quite. 1500. 1600. 1800. I'm going to call that good enough. Okay, so there's our initial state of our wind barbs, looking at U10 and V10, which is wind on X and Y, 10 meters above the ground. I'm going to go to my appearance tab, and well, actually, if I look at my variables, we're coloring them by temperature, which doesn't make a lot of sense. Typically, we want to color our wind barbs according to the wind speed. These will lengthen with increased wind speeds. You can see there's some very short ones that have low wind speed and some very long ones with high wind speed, but coloring them by wind speed is typically what we want to do. So to do that, we can see if I look at my color map variables, there is no wind speed variable. And so I have to create it. So I'll go to the tools menu, go to Python variables. And from here, I'm going to create a new variable. I will call it speed. Click OK. And then once I do that, I get a list of the 2D and 3D variables that I want to input into my script in order to create an output variable. So I'll scroll down, and this is going to be a two-dimensional wind speed. So I'll go to my 2D variables, select U10 and V10, create a new variable. I'll name it the same thing as the script. The script's name is speed. My variable's name is also speed. And then I believe, yeah, west, east, south, north, the unstaggered WRF grid is what I want. Vapor comes with a module called Vapor Utils, which is handy for doing this kind of thing, especially with WRF files. And so I'm going to do from Vapor Utils import everything, and just to show you guys what that file looks like. When you install Vapor, vaporutils.py, it's going to have all these Python functions that you can use to do things like take a variable and put it onto an unstaggered grid with this staggered to unstaggered grid function. You can do things like find curl and the magnitude of two different variables, and that's what I'm going to do here. So I believe the script I want is just going to be using the mag function on U10 and V10. I will test it, test passed. This is interesting. Hung up on something. I wonder if it's OS X scrutinizing what Vapor is doing again. But one way or the other, we got back unscathed. So I will save that script to my session. And this is a good, well, after I turn my speed variable on, I'll get to what a session is. So now that we've created a speed variable, I can come down here, select speed, and instead of temperature, we will be coloring according to our new variable. I'm going to mention what a session is real quick, because as you work with Vapor, you're going to want to save your state, just like you would in Photoshop or Microsoft Word or any other desktop application. So I can go to the File menu and save my session, give it a name. I can call this test, save it, and then later on I can spin Vapor up and then open that session and be at the same state that I left off. If Vapor ever crashes, what you can do is reopen Vapor, open a session, and then in your home directory, there will be a file called Vapor Autosave. Every 5 changes you make in Vapor will write to this Vapor Autosave file so you don't lose your work. So just keep that in mind if Vapor ever does crash, because it does happen. All right, so I have my new wind speed variable for my barbs. I will point out the fidelity controller is now enabled because with this data set we converted to VDC. I can bump the fidelity to medium and high, but it's not going to be evident how much the data is changing with the Barb Renderer. So I'm just going to leave it on low for now for speed reasons. Go to my Appearance tab. I'm going to pick a different color map. I think, gosh, I typically use ice, is it? Yeah, this one's called ice. And then I'm going to make the high wind speed values more white, and then I think the low wind speed values are dark enough. I'm going to scroll down a little bit, and here I can control other settings for the Barb Renderer, like how many barbs are on the X, Y, and Z axes. So if I crank that up to 50, let's see how long this takes. If I crank this all the way up, you can see how busy it gets really quick. So one thing you can do is decrease the thickness with these controllers and the length scale to make them smaller. Well, that's probably too short. I don't know. Let's see. I'll just call this 0.2 for now. Okay. And one thing I typically like to do with the Barb Renderer is turn off lighting. You can see there's these shadows on the wind barbs. And let's see. There. So if I go to my annotation tab, here's where I can add color bars for each renderer. If I click show color bar, this should give me a color bar down here. But you can see these shadows kind of give it a different coloration than what we see in the color bar. based on where the camera is and where the light is coming from, will affect the actual color of the barb. So what I always do with my barbs is I disable lighting, and now the barbs will have a truly representative color of what this color bar, what is shown in this color bar. Gosh, I think we have about 30 minutes left. So I think what I'll do next is quickly demonstrate the slice renderer. So I will turn this off. And I mentioned the atmospheric rotor. So I'm going to try to find that with our slice. The first thing I'll do is click on New. Again, this is marshallmet.bdc. Double click on Slice. And then by default, we will have a slice that encapsulates a XY plane at the middle of our domain. I'll go to my geometry tab, and I think we're going to run into that offset from the ground issue again. But again, in the geometry tab, we'll be covering or controlling where we are rendering to in space. And the slice renderer has this orientation mode. You can rotate it about the X, Y, and Z axes, or you can control which direction the normal orthogonal to the plane is pointing. I find rotation to be more intuitive. So what I'll do is rotate it about the X axis. And then let's see, is it, the slice seems to be relatively close. There is a little bit of a gap. So I'll come down and I will translate it. Gosh, what was it? It's not going to be minus 1800, is it? It looks like too far. Yeah. So I'll just try minus 900 and I don't know, maybe 800 and call it good enough for demonstration purposes. I can come back up to my rotation controls and I can offset the slice from its center. So if I drag it up along the front range, I can go back and forth. Or if I wanted to rotate it about the Z axis and get kind of a diagonal perspective, I can edit the Z field and then change the offset of my slice like so. Let's see, I'll go ahead and reset my Z field to 0. And let's see, what variable are we looking at? We're looking for the rotor. So one of the variables that might show us where the rotor is W, where the winds would be kind of contrasting. Like right here, we have positive, or is that negative? Go to my appearance tab, yeah. We have winds around 10 meters per second. I zoom in a little bit more in this red area going vertically 10 meters per second. In this blue area, they're going down. So there might be a rotor right in here with ours that we can see with our slice renderer. I'm gonna go to my variables tab. And again, we're looking at low fidelity. So I'm gonna turn this up to high and see if there's there should be some more, an increased resolution on our slice. But you can see it's taking much longer because when we were at low, we were looking at a 63 by 63 by 5 grid. Now that we've changed it to high, I believe the grid is roughly 500 by 500 by 60, I'm guessing. And so that's going to take longer to render, but you can see the fidelity is much higher. And so if I was to create an animation, this is how I would want to look at it. I think what I'll do next, for the sake of time, I do want to get to the Python API, but I also want to demonstrate the flow renderer. So I'm going to create a new flow renderer and get through that real quick. So click New, click Flow, click OK. And like the Barb renderer, the flow renderer will select your U, V, and W fields by default according to the variables that start with your U, V, and W, or your X, Y, and Z field, I should say. And you can see the flow renderer is by far the most complex renderer in Vapor. We have two additional tabs, the seeding tab and the integration tab. I'm not going to worry about the integration tab right now, but like other renderers, we have variables, appearance for how we're rendering, and geometry for where we're rendering to. I'm going to start off by reducing the geometry tab, or reducing the Y field extents. You know what I'm going to do? Instead of doing this manually, I should be able to copy a region from another renderer. And so I've already reduced my volume renderer. If you guys remember doing that for the smoke, I can select this. I know it's kind of hard to read, but this is the volume renderer that we created earlier. Go ahead and copy it. And my extents should now match roughly what our volume was. And you can see our red box is in that same area. So for the flow renderer, most of your time is going to be spent in the seeding tab, where you can dictate whether you're doing path lines or streamlines with this drop-down box. I'll be doing streamlines, which is, again, time invariant lines that follow the vector field. You can go forwards, backwards, or bidirectional in the direction of the flow that you're integrating. Integration steps is kind of a fuzzy number that you might have to play with. If something isn't advecting as far as you like, you can increase the steps. Vector field multiplier, sometimes data sets have a mismatch between the units of their domain and the units of their wind field. So if you have a wind field in kilometers per second and your domain is in meters, you can edit the field multiplier to make those two values match. And then there's periodicity controls, which kind of control if you have a flow line that goes out one of the sides. If a flow line goes outside of the domain, it will then reappear and start advecting from the other side. Kind of like how Pac-Man can leave the right side of the screen and then re-enter the left side of the screen. That's kind of what periodicity is. The seed distribution settings over here. There are several ways to generate what we call seed points, which is the origin from which your flow lines begin. You can create them in a grid. By default, we have 5 by 5 by 1 on X, Y, and Z. And if I just turn flow on, you'll be able to see what that looks like. So let's see. Let's turn off our slice just to get a clearer view. So right now, is that right? Right. So yeah, I see what's happened here. Right now, we're not seeing a 5 by 5 by 1 grid being drawn, because when we go to the seeding tab, we get another red box. And this red box dictates where our seed points are beginning. Geometry is where we're rendering to, and we're only rendering the seed points within this red box. But the seeding tab is dispersing these seed points throughout the entire domain. We're just not rendering them because we've reduced our region and geometry tab. So I'm just gonna, let's see, I'll go ahead and undo what I did earlier and unconstrain our geometry. And from here, it may or may not be easy to see the 5 by 5 grid. I'm gonna scroll up and I'm gonna reduce my integration steps so they're shorter, even shorter. Let's do 5 integration steps. And that's too little. 25. Still a little bit long, but you can kind of see I've got 1, 2, 3, 4, 5 on my x-axis, 1, 2, 3, 4, 5 on my z, and then vertically there is only 1. So if I'm going to try to find my rotor, let me think about how am I going to do this. I'm going to start by just doing, for the sake of computation, 1 by 1 by 1 from the center of my domain. And if I check my variables out, I am at low fidelity. So for the sake of time, that will render quickly. And I'm going to go to my appearance tab. Instead of coloring this by another variable, I think, yeah, we're looking at our flow lines colored by pressure right now. I'm going to come down here and do a constant color. Default is white, good enough for me right now. Make it a little thicker. Turn on lighting. I typically like to light my flow renderer more so than my barbs. And then I'm not going to get into all of the widgets and parameters, but I think that's good enough for me right now. So what I want to do is, if I'm going to try to find this rotor, I'm going to turn that slice on. We have our discrepancy in our W field over here. I'm going to go to my flow renderer, go to the seeding tab, and then down here at the bottom, there should be an option to control where the rake center is. So let's see, hopefully this doesn't take too long. I'm going to bring the rake center where my flow line is originating over back to the left. And then I'm going to move it up on the Y and try to intercept where this this rotor might be. Bring it back. Right now it's behind the slice renderer. why don't I just go to my slice renderer and apply some opacity to it so we can see through. I'll grab the middle of this bar and I can drop that down and then mask out all of these more densely populated variable values so that we only see the tails. And you know, I think I'll just give it more of a sharp transition. I don't know, something like that, I guess. It takes a lot of fussing and I don't know, a lot of eyeballing to get these color bars right. But now that we can see through it, we can see our flow line. I'm going to go back to my flow renderer and go to the seeding tab and keep on messing with this flow rake center parameter. And ideally, what I would hope to see with this rotor is the flow lines just dipping down and then swirling like crazy right here. If I go to the seeding tab, let's make it a little longer by adding, let's do 50 integration steps, which will make the flow line longer. And then what I'm going to do is I'm going to add more flow lines to the z-axis. Let's do 10 on z. So we'll have a stack of flow lines going up through elevation. So I'm not getting the swirls that I was looking for, but you can kind of see the, I don't know, just the shape of what the winds are doing, which if I go back to the, you can kind of see this hump to the east of where the fire is. And if I go back to these photos of the Marshall Fire, you can kind of see, well, you can kind of see there were these ripple effects on that day. And it's kind of what we see there. I'm getting a message that my MacBook is about to run out of batteries. So let me plug it in real quick. It would be bad for my MacBook to run out of batteries right now. Okay, so I don't know. I hope that gives you guys some kind of comfort with how Vapor is laid out. All of the renderers are essentially doing the same kind of thing, and they operate in the same kind of way by having these tabs: variables, controlling what you're rendering, appearance, how you're rendering it, geometry, where you're rendering it. So once you get comfortable with one renderer, it should be fairly straightforward, unless you're dealing with the flow renderer, it should be straightforward to navigate all of the others. I think that concludes the Vapor GUI portion of the tutorial. The last thing I do want to touch on is the Python API. And so the Python API, I'm going to demonstrate through use of Jupyter notebooks. And so once we release Vapor 3.7, we're hoping to host Vapor's Python API on this repository called Conda Forge. And if you're not familiar with what Conda is, it's basically a environment manager for Python that allows you to have different environments that you can easily select from one environment to another. So for example, if you need a version of matplotlib to do task X, but you need a different version for task Y, you can swap your environments without corrupting or doing any cross-contamination. And so once we release 3.7, we're hoping that getting this API that I'm about to show will be as easy as conda install Vapor. And let me make this bigger so you guys can see it. And I'll clear the screen, but conda install Vapor should be all you need to do, but we're not hosted yet. We have to release before we do that. So if you would like, I can, if you guys want to play with this before we release, let me know, go to our forum, and I can give you an installer and tell you how to set it up. Once you install the installer that I give you, or you install it from Conda Forge, basically in this long directory will be a series of example notebooks that I'm going to be working from. And so to kick this off, I will do Jupyter notebook. I forgot the E notebook. There we go. And here's my browser with all the examples that we bundle. You can run these through Jupyter or you can run them through Python. I'll show you both. But I'm going to do workflow example.ipynb, And this will show you how, through Python, you can create renderings in Vapor. Let's see, I will restart and clear the output. Okay, so the first thing that you'll have to do, or that this does, is there's a few imports you have to do from the Vapor module. You have to import the session, which allows you, like I showed earlier, to save and load different sessions. The renderer module contains all the renderers, 2D, volume, flow, etc. The dataset module controls data I/O. Camera is where in space your camera is being viewed from, and utils is kind of just a miscellaneous hodgepodge of different utilities. So I will kick it off by running that import and ignore that warning. We identify the current version of Vapor, current version of Python, and OpenGL has been identified. So that means we are good to go. I will now run the second example where we create a new session. And then there is an example data set that we bundle with our Conda installer, and we're going to be working with that one today. But if you wanted to use your own data set, this is the parameter where you would put that argument. So the next thing we'll do is print the metadata in our data set. And we're just going to list time coordinate variables, dimensions, and the data variables. We have U10, V10, and a 3D variable V. And here are the attributes of those variables. And I guess the data range at the very end. Next thing we will do is render the first 2D variable, which I believe is U10, as a pseudo color. And basically, we will get the data var names. I think this will be U10. We'll find out when we print this out. And then we will create a new renderer, call it ren. And from our data module, we will create a new renderer, which is renderer.2D data renderer. We will set the variable name to what we found up here. And then we will get the transfer function, get the primary transfer function, and set the minimum map value to -1 and the maximum value to 1. And then we will get the camera and then draw with the show command, and then finally delete. So once we do that, here's what we get. And if you were running this just through pure Python, you would get a pop-up window that would have this image in it. I can show you that real quick. And here we go, doing the same thing, but with barbs. We create a barb renderer, data.new renderer, specify the barb. We set the dimensions to 2. Like if you remember earlier, we could do barbs with 3D variables or 2D variables. We're doing 2-dimensional variables, U10 and V10, and setting the line thickness like we did in the GUI earlier. And voila. And same thing with flow. Create a new flow renderer, give it the 2D variable names, and then show it. Huh, that's interesting. That should be showing something. So I wonder if I misclicked or edited something. Well, I'll just move on, hopefully more gracefully, with the volume renderer. Same idea, create a new volume renderer, select the variable. And here's how you set the opacity list. So these are the control points. We have the first control point being fully opaque, second control point being transparent, third being transparent, and the fourth being completely opaque. And these are just evenly dispersed control points, like we saw along our histogram. There's that, with color bar at the bottom. And then scaling the z-axis. From the data set, we can get the transform and then get the scales and then modify those scales. So the scales is like, I guess, a triplet on X, Y, and Z. So scales of 2 would be the z-axis, multiply it by 0.3, and then we set the scales according to that value. And here we have our squished volume renderer. Up here it was more of a cube we were looking at it in, and here we are seeing it squished. And then finally, adding axis annotations, simply enabling them. And here's our squished volume with annotations. And then here's where we would save that session file if we wanted to open it in Vapor, or maybe open it through Python another day down the line. So that's how things worked, I guess, through an interactive demonstration with Jupyter notebooks. I also want to show you guys what this looks like in pure Python. So if I go to, let me clear my screen. So I'm in this directory, in the example notebooks directory. If I go up one into examples, here are all the examples in pure Python format. And I think what I would like to do is if I do, I'd like to show you guys, if I look at my flow example, here it is in pure Python. If you guys are ever wanting to know, like, so I've shown a bunch of functions and not all of the functions are covered in these examples. So let's see, how would you do this? There's a help menu. So if I do this, 25, I'm just going to go ahead and mangle this for a second so I can copy it. Okay, I'm going to copy those lines. And basically all this is doing, is this going to work? I think this will work. No, it won't. There, that should work. So if I just copy these lines, basically all they're doing is opening a new session and creating a new data set and then creating a new renderer. Actually, let me see. I might be able to just call help on renderer.flowRenderer. So if I go to, if I quit, and then I do Python, wait, let's see, which Python, okay, conda env list, conda activate vapor. Now I go to Python, and then let me just help on, is that gonna work? No, I need to, let's see, for example, okay, where was I? There, okay, so if I import all my modules, I should now be able to help on Flow Renderer. And here's where I have all of my documentation for the different functions that are available to me through the Python API. Get, flow direction, etc., all the getters, and all the associated setters for all the parameters. And so that's the gist of it. I think I have about 5 minutes left, so I'd like to open the floor to questions if anybody has any. And thank you guys once again for joining. I guess we can do questions through the chat, which I've kind of neglected to look at through the presentation, but let me see. Okay, let me see. Should I start at the top? We can hear you, yes. The WRF file seems to contain a single or only a few timestamps. Do you suggest time splitting WRF out files? You know, every time I work with WRF, it's always one time step per file. And I don't know, did I forget to cover how to animate through time as well? There's these controllers up here. And I guess since I'm done demonstrating Vapor, I can go ahead and click them. But before I do that, I'm going to go to this capture menu and capture an image sequence and capture PNG files. Once I click on that, I'm going to be asked to give a name. So I'll do this. I'll call it test. And that's going to spit out a image file for each rendering that Vapor does, whether it's through a change of a parameter, a rotation of the scene with your mouse, or by animating forwards in time. And so by clicking this play button, I'm now animating in time, and Vapor's now taking images named test that are suffixed with a numeric value indicating their timestamp. And so, yeah, this is going to take a while, but I'm done demoing, so that's going to be okay. But yeah, that's the answer. I think I've always seen WRF have one time step per file, but it shouldn't matter as long as your variables are associated with a time coordinate variable that that has correct units according to the CF conventions. And I didn't get to the CF conventions today, but all that documentation and a YouTube video is on our website. So you can find it there under the Getting Data into Vapor menu. I would really like to see an example with map outputs. I'm not sure what map outputs are. If you're referring to something other than the image renderer, maybe you could elaborate in the chat. Oh, and then Lily noted that my battery was going down. So thank you, Lily. All right, Vapor does a lot more than last time I tried it. Thank you, and you're welcome. When I last used Vapor a few years ago, it didn't function for laptops that only have a trackpad and no mouse. Is the new version going to be usable on laptops with a trackpad? Technically, you can use it with a trackpad. I never would recommend it though. I believe, every operating system has different keyboard layouts. OS X has the command, control, option keys. Windows has, the window key. Some of those hotkeys can be used. I don't know if we're consistent on this across platforms, but you can get away with doing translation, rotation, and zooming through it with a trackpad through the use of those specialized keys. But I never would want to do it. You just have so much more precision with a mouse. Even if I knew what the hotkeys were to activate the different functions for a trackpad, I still would never want to do it. Okay, so moving on. Thank you, Scott. Where and when will this recording be available? I think I might be able to get it up today on our Vapor YouTube channel. So if I go to vapor.ucar.edu, and let's see, my documentation, there's going to be a link in our documentation to our YouTube channel. So if you go there, here's all of our uploads. I guess it's been 2 months since my last one. So yeah, I'll get this one up today. And yeah, that'll be up there for your cross-referencing. And yeah, I'll try to timestamp as well. Give it relevant links and try to timestamp important points in the video. Are there any options similar to speed point advection like we had in Vapor 2? Speed point advection. You may be referring to rendering advection with bias towards a certain variable. So when and Vapor is totally hung up. I can't even open it right now. And my laptop sounds like it's about to launch off my desk. But I think what you're referring to is rendering streamlines or path lines with bias, like allocating the position of those streamlines and path lines with a bias towards a certain variable. So what we did, we distributed our streamlines along a grid. I think we ended up with an XYZ grid of 1 by 1 by 5 on X, Y, and Z. You can also distribute, for example, if you wanted 50 streamlines originating from areas in your data field that have a high speed value. So say you derive speed, you can distribute 50 streamlines where the speed is high, or distribute those with a negative bias where the speed is low. And so what you're going to want to do for that is, instead of using a gridded seed distribution, you're going to want to select random seeds with bias. Well, you'll get to randomly distribute those seeds according to the bias variable that you select. I hope that answered the question, but I'm not sure. Feel free to follow up on our forum, which I showed earlier. Looks like Vapor still cannot support SE output files. What is SE output? Are there any plans to accommodate these data files? I don't know what SE output files are. So I gotta say, if you could defer that question to the forum, we could either figure out how to get that data into Vapor, or write a new enhancement request that we could maybe develop for version 3.8. Can we invert the z-axis if our data set has z-coordinate values positive? Ocean model, yeah. So this is, I wish we could. What I had to do for the video that I was showing at the start, if I open up my PowerPoint presentation, let's see, yeah, this ocean model right here that I guess no one can see there. This is upside down. So what I had to do here is just basically rotate the scene until everything was upside down, and that kind of did the trick. What I really wish we had was better support for different Z coordinate fields, but that might be something coming up. And I'll say for the record, user feature requests get a lot of traction, a lot more traction than I guess my own feature requests. As a developer, we try to listen to our users as our main requirement resource. So if you want to see that done, it's more likely to happen if you post on our forum and we can write a GitHub ticket that we can track and follow along with. But I agree, that is something that is kind of painful. It's not fun flipping this thing upside down each time I want to work with a new similar data set. For data sets with different time indices, can it be manually synced? Or is there a way to manually override the time index of a data set? So for netcdf files, basically you have to specify all variable time steps through the time coordinate variable. And if that isn't making sense, if I just do an nc dump, cd into data, cf, these are my cf compliant netcdf files. Go to WRF data, and I go to may control. This is the tornado data set. If I do nc dump -h on 24, may control 001, or something like that. Basically, this guy right here, the time coordinate variable, the variable that is a direct reference to the time dimension, is how you're going to synchronize your variables amongst each other. So this is seconds since 2000, January 1st. And that's the unit. The axis is t, and the long name is time. As long as you have something like this, and in your files, if you do a nc dump dash variable, and then time, 4002. So for that file, your time value is like that. That's how you got to do it for netcdf and Vapor, or how you would go about overriding. So I hope that's helpful. How to install Vapor Python API. Right, so we haven't released Vapor version 3.7 yet, and we need to do that in order to be hosted on CondaForge. If you'd like to install it, post a message, or maybe I'll post a message on our forum where you can download some installers that I'll generate manually. And if you'd like to download and install that, you can give us feedback that way. So yeah, check out our forum, vapor.discourse.com, I think. If I go back, let's see. If I go to our documentation, get help on our forum, follow this link, and I will put some files for you to download and install and some instructions up there. Okie dokie. Is it possible to do a one-on-one Zoom consult for help? The functionality is so expansive that it's hard to even know where to begin with all the options, especially when we have very large data sets. Yes, definitely. Give us a request on our forum, and then we can set something up and just do a quick screen share. No problem. Ajit, I meant translating the position of seed point, translating the position with the velocity field. I think you might be referring to path lines, which let me just, best to just show a visual example to see if we're talking about the same thing. This is a tornado scientist. Gosh, let's see, YouTube, the WRF. WRF, let's see if I can get lucky and find him using Vapor. Presentation. Let's see, mute it, and then scan. Not doing path lines yet. Here we go. Here's path lines. So here's the path lines that are time variant following the velocity field, as time changes. just one more time. So for that, you would want to use path lines. Streamlines, again, are time invariant, just following the vector field at a single time step. Spectral element, not sure what that's referring to, but I'll just go down. And if you guys have any more questions, again, hit us up on the forum. Sorry, my question was not clear. I want to display a time sequence of data values from 2 data sets. Their time values are different. Yes, what you're going to see then, right? So if you have 2 different data sets and they have like some kind of interleaving between time steps, basically what you'll see in Vapor, yeah, I shouldn't have clicked play because Vapor is just totally bogged down. But basically it's just going to, how do I explain this? It's going to iterate through all the time steps, but you're not going to see the renderers for both data sets change for every time step. The renderers will only change at time steps where new data is loaded from the disk, if that makes sense. So it might look a little jerky, it might look a little unsynchronized, but Vapor will iterate through all time steps and just load in render data as the time series progresses. Okie dokie. I think that's all the questions and we are over time. So again, guys, if you have anything to follow up on, hit us up on the forum. I'll get this video up hopefully sometime today. And thank you again for joining. And yeah, if we have another tutorial, we'll send you an email and I hope to see you again soon.